So in the first video, we were talking about visualization and summary statistics for one quantitative variable, and now we're going to talk about the bootstrap in particular. The bootstrap is this procedure that lets you pick yourself up by your bootstraps to create a sampling distribution when you only have one sample. So what we're going to do is we're going to resample from our existing sample, and we're going to use those bootstrap samples to generate sample statistics and therefore a sampling distribution. So in order to do this, we need a couple new verbs. One of the verbs that we need is specify, and the other one is generate. So in this case, I'm going to take GSS, then specify that my response is the highest year of school completed, then generate one rep of type bootstrap. So usually you do more than one repetition. Rep stands for repetitions, but we're just going to start with one so that we can see how this is working. And then I'm going to assign this into the name bootstrap sample. So if I Control Enter on this, now nothing prints out in my console, but I get a new object in my environment. And let's look at it and see how many observations and variables it has. So my original data set had 2,345 observations of 45 variables, and this new data set has 2,345 observations of 2 variables. And we can click on it and see what it looks like. So it has 2 variables. One is called replicate, and the other one is the highest year of school completed. And so these are samples from the original data set with replacement. So the bootstrap sample always samples with replacement. So we might see a particular person's highest year of school completed showing up more than once here. And right now, the number for replicate every single time is 1, because we only did this one time. So it has the same number of observations as our original data set, but only 2 variables. The highest year of school completed, and a new variable called replicate. All right. So we could make a histogram of this bootstrap version of highest year of school completed. Again, you could pause the video and see if you can figure out how to do that before you go on. Okay, now I'm going to do it. So I'm going to ggplot parentheses, and now I need the name of my data set. And I don't want to use the GSS data, now I want to use my bootstrap sample data set. I'm still going to use the geom histogram, and I'm still going to need an AES, short for aesthetic, and I'm going to say x is equal to, and then I need to put in the name of the variable that I want it to use. So again, it's going to be highest underscore year underscore of school completed, and I can Control Enter, and it's going to complain again, so I'll set bin width to be 2. All right, so I'm going to go back up and I'm going to run my original histogram of my GSS data. So here was my original histogram. And then here is my bootstrap sample histogram. So these distributions look similar. Yes, they are similar, but not exactly the same. So if we look at our original data set, it looks like there were about the same number of people in this year 12 category, but in our original data set we had a couple more people who had completed maybe 16 years of school and a little bit fewer here. So that's because we're sampling with replacement. So we might get some people more than once and some not at all. So it's slightly different because it's a random sample. And then the other question is, does your histogram of your Bootstrap sample look the same as mine? And the answer, I'm pretty sure, is no. So I'm going to put no here because your histogram is from a different random sample. So you did your Bootstrap sampling from GSS and you got different people in your one Bootstrap sample than I did. And so your histogram will look similar. It'll look similar to the original one and it'll look similar to my Bootstrap histogram, but it won't be exactly the same. So this brings us to a point about randomness in R. So Bootstrap samples are random, and that's good because we want them to be like random samples from the population. The problem is that every time you run the same code, you're going to get a different sample and then a different histogram. So if I went up and ran my Bootstrap sample code again, and then I ran my histogram code again, my histogram looks different. And when you knit your document, all of the code gets run as the document gets knit. And that means that the histogram that you saw when you were working isn't the same as the one that's going to turn up in your knitted document. And every time you knit your document, it's going to change. So that can be really frustrating. The way that we fix that is that we set the seed for the randomness. So there's this function called set.seed, and you just run the function with your favorite number inside. So I often use 42, the answer to life, the universe, and everything, or I'll use the day's date, like 03/19/2020, but it doesn't matter what you pick. Some people use their birthday, etc. And so if I run that, I don't see anything happen, but it's going to put the pseudo-random number generator that's in R at the same starting point so that every time your randomness is going to be kind of predictable. So let me show you what that means. So if I set my seed to be 42, and then I take a Bootstrap sample, and I make a histogram of it, and then I take another Bootstrap sample, and I do the histogram of it, it's going to look different. So these two, if I flip back and forth, they don't look that different, but they are different. So every time I run that code, it's going to be different. But then if I set the seed back to 42, and I take a Bootstrap sample, this is the same histogram as two plots ago. So not this one, but it's the same as that one. So after the seed is set, then the randomness will be the same. And what that means is if you set the seed at the top of your document, then every time you knit the document, it will turn out the same. So I could copy this code and I could scroll all the way up to the very top of my document, and I could put it maybe in this setup chunk underneath my packages, and then that'll make it so that when I knit my document, the seed gets set. You only ever have to do that once in your document, so usually you put it in the setup chunk. So that's something that you are going to want to do for your lab, for your real lab. All right, let's go back down to where we were. So we've set the seed to make our lives easier when we knit our document. Now we're going to talk about a Bootstrap distribution. So just one Bootstrap sample is not very interesting. If we're going to make an interval, we need to repeat the Bootstrap sample process many times, where many is usually at least 1,000 times. And we don't really want to store all those 1,000 full data sets, so we're going to add another verb to the end of our pipeline. We're going to use the calculate verb. So I'm going to do the same thing. GSS, then specify response is highest year of school completed, then generate 1,000 reps of type Bootstrap, then calculate stat equal mean. So the statistic that I want to compute is the mean, and then this whole thing is going to get assigned into something named boot. So if I control enter, now it might take a second to run because it's doing it 1,000 times, but you should get something new in your environment. And so now this data set has 1,000 observations of two variables, and I could click on it. And this time I have my first replicate. So that was, it took a sample with replacement of size 2345, and it computed the mean and it put it here. And then it took another sample with replacement of size 2345, took the mean, and put that mean here. And it did that 1,000 times. So that's why I have 1,000 observations in my data set. So it has 1,000 observations, which correspond to the 1,000 Bootstrap samples we took. Two variables, replicate, which is the sample number, and what's the other one called? Stat, which is the mean of the Bootstrap sample. So now we can look at the distribution of that statistic, and we're going to do a ggplot. Our data set will be called boot, and then we'll do a geom histogram, AES, x equals stat. So we're going to make a histogram of all those means. And if I control enter, now I get this kind of histogram. I could set the bin width, but it's not going to make sense to set the bin width to be 2. If I set that, I'm just going to get a big block. So that's way too wide. So I think maybe like 0.1, 0.01. So this is a pretty different distribution. This does not look like our original histograms. No, it's shaped very differently. And that's because this is a Bootstrap distribution. So it's a distribution of means of the Bootstrap sample of ages. So we could see where it's centered. It looks like it's centered around 13 point something, but we could compute the mean of that parameter. So let's do this. We'll take the boot, and then we're going to summarize mean of, and the variable is called stat. I could control enter. So the mean is 13.7. And does that make sense? Yes, because a Bootstrap distribution is always centered at the original sample statistic. So our original sample statistic was 13.7, so that's where our Bootstrap distribution is going to be centered. So the center of the distribution isn't super interesting to us. What we're looking for here is something about the spread of the distribution, and in particular, we want to compute a confidence interval from it. So if we wanted to, we could just use the 95% rule, and we could eyeball a confidence interval that contained the middle 95% of the distribution. Just looking at it, I think like 13.65 to 13.85. That's my guess. But we want to be more precise. So we're going to use the get CI function for get confidence interval. And if you get CI of that set of 1,000 Bootstrap statistics, then you're going to get a confidence interval. And what it gives you is, by default, a 95% confidence interval. So it gives you the point at which 2.5% of the distribution is less than that value. And then it gives you the place where 97.5% of the distribution is to the left of that value. In other words, 2.5% of the distribution is to the right. So this is a 95% confidence interval based on that distribution. And then we could interpret that output. We are 95% confident that the true mean number of years of school of Americans is between 13.6 and 13.8 years. So that would be our interval estimate. And that's what the Bootstrap allows us to do. even though we can't go out and do another large survey like the General Social Survey, we can pretend like we've been able to take many samples from the overall population, compute statistics, and then create a sampling distribution.